Now we consider the mean value theorem for vector valued functions. Okay. Unfortunately, we can only have a mean value inequality, not equality. So suppose omega is an open subset of Rn, and f is a C1 continuously differentiable real-valued function in omega, and a segment AB lies in omega. AB. Then we have the mean value theorem. By the mean value theorem, there exists a C in the segment AB such that FB minus FA is the gradient of Fxc, inner product which B minus A. But as you it is not difficult to see that the gradient of Fc is d1f c, dnf c, and of course the gradient, if we write B minus A as a column vector, then the gradient, because you want to take inner product, the gradient has to written in gradient in column vector. So the inner product is the transport, that is the row vector multiplied by the column vector to obtain the inner product, which is a real number. So you see that this is precisely f prime c. So this can be written as f prime c B minus A. So this form of the mean value theorem is exactly the same form for single variable functions. Okay. Can this be true for vector valued function? A natural question. Because the mean value theorem is very useful. Based on the mean value theorem, we can have many useful conclusions. But can we obtain the same result for vector valued function? This is a question. Unfortunately, the answer is no. Why this is no? Because a natural idea to generalize the mean value theorem to generalize a result for real valued function to vector valued function is to apply the real valued result to the components of the vector valued function. So for every component of f, for every component of this vector valued function f, for fi, we have, by the real valued function result, we have c such that fib minus fia is the gradient of fi c b minus a, inner product with b minus a. But for different I, this c might be different. So you could not find a common c for every I. If you can find a common c for every I, then fb minus fa is f1b minus f1a, fnb minus fnm a. So this can be written as f1 c if the c are, if you have a common c for every I. Okay, so this is the f prime c b minus a. But unfortunately, for different I, the Cauchy might be different. So this could not be written by f point Cauchy. So this is Cauchy 1, Cauchy 2, Cauchy m. Every component you have a Cauchy. Okay, this is the problem. So for vector value function, you could not have a mean value in theorem in equality form. Okay. I urgent you to construct example. In that example, the Cauchy does not exist. Okay. So in general, we could not expect equality, but we have a weaker version of the mean value theorem, which is sufficient for many purposes in our future. Okay, this is the mean value inequality theorem. No, I don't like red. Let omega be open set in Rn, and f from omega to Rm is C1, continuously differentiable. And as before, a segment is contained in omega. The result is that then there exists a Cauchy in the segment, such that the norm of fb minus fa will not greater than the norm of f point Cauchy. F point Cauchy is the derivative of f at Cauchy. This is a matrix, therefore this is a metric norm, then b minus a. Okay. This is the mean value theorem for vector valued functions, but the result is not an equality but an inequality. Okay, so here we assume that f is C1. C1 means differentiable. Why? Because f is C1. F C1 means every fi is C1. Every fi has continuously continuous derivatives. Previously, we have a theorem. If a function whose partial derivative functions are continuous, then the function is differentiable. So every fi is differentiable because the derivative of fi are continuous. So fi are differentiable. Then in our previous lecture, we know that f is also differentiable. We have a previous result saying that f is differentiable if and only if all the component functions are differentiable. Okay, so this is the case. So the assumption that f is C1 means that f is differentiable. Therefore, the derivative appears in the result. Makes sense. So now we prove this theorem. The idea to study multi-variable function is to try to convert the problem into single variable function, as we have seen many examples before. Okay, the partial derivative, the definition of partial derivative itself is a typical example of this idea. Now, the study of vector valued function, a very useful idea is to try to convert the problem into problems about real valued function. How to get real valued function? A useful idea is to taking inner product. Okay, so prove. We defined a function phi phi x is fb minus fa. This is a vector in Rm. We take inner product with fx. Then phi is a constant function. Phi is the inner product of a constant function and a differentiable function f. Therefore, by our previous result, phi is differentiable. Actually, phi is C1 omega, real valued, and the derivative of phi at any x is the transport. Remember our transport result? After we introduce the differentiability, we prove the computation rules for derivatives. We have a result about the real valued function obtained from the scalar product or inner product of two vector valued functions. Now our phi is the inner product of two vector value functions. This is a vector value function, constant function, but the value is a vector. And this is another vector valued function. So phi is the inner product of these two vector valued functions. Therefore, we can apply the result. So the derivative of phi and x is the transport of 1 multiply the derivative of the other function plus the plus the transport of f multiply the derivative of the other factor. But the other factor is constant. fb minus fa is constant. Therefore, the derivative of the map, constant map fb minus fa is 0. Therefore, this term will not appear. So the derivative of phi prime, the derivative of phi is given by this formula. Now, because of phi is a real valued function, so we can apply the mean value theorem, Lagrange theorem to phi. We obtained a Xi in the segment AB such that fb minus fa square, this is precisely phi b minus phi a. Okay? And now we apply the mean value theorem for phi. Phi b minus phi a will be the derivative of phi prime Xi b minus a. But phi prime Xi is fb minus fa transport f prime Xi b minus a. And of course, this will not greater than this is the inner product of fb minus fa, which f prime Xi b minus a. This inner product will not greater than the norm of fb minus fa, because this was multiply the norm of f prime Xi b minus a. But for the f prime Xi b minus a, we have this will not greater than fb minus fa copy, and phi prime f prime Xi b minus a. This is our last computation. For this, we apply the property of the metric norm. So this will not greater than fb minus fa. The norm of f prime Xi, the norm of b minus a. What's the left hand side of our computation? The left hand side is the square of the norm of fb minus fa. So all this together is that fb minus fa square not greater than blah blah, not greater than our final result. Now you cancel one of the fb minus fa, we'll get the norm of fb minus fa is controlled by the metric norm of f point c b minus a. So this proves the mean value inequality for vector valued functions.